Hi, here is the recording for weekly tutor session 1, and we will go through the weekly problem set 1. Okay, let's begin. For the first question, the first part of first question, we want to use the piano axiom to prove that a plus b equals to b plus a. And the definition of plus is here, and here is the only thing we can use. So before proof a plus b equals to b plus a, I want to prove two lemma first, as we want to use that later. So the first lemma is a plus sb equals to sa plus b. We want to use induction to prove this one. For our induction, here we have two variables a and b. We can just set one of these two variables to 0. So let's set b to 0. So our base case is a plus s0 equals to sa plus 0. Is that correct? How can we show that? Here we can simply try that a plus s0 equals to sa plus 0 according to the definition of plus. And also use the definition again, we got sa. And also use it again, we got sa plus 0. So we know that the base case is correct. How can we do the induction? What is our induction hypothesis? Here it is. Suppose we know that a plus sb equals to sa plus b. Then what about a plus ssb? What's this? Sorry. Again, I want to use the definition of plus. So we can change this one to sa plus sb. And then what can we do? Here we found a plus sb, which is in our induction hypothesis. So we can try to change the format of it to sa plus b. And then we just reuse the definition of plus, and we can get sa plus sb. And then we are done. We are prove the lemma 1, which is a plus sb equals to sa plus b. Okay, then the next lemma I want to prove is that I want to show that a plus 0 equals to 0 plus a. So the base case is really easy. We just set the a equals to 0, so we get 0 plus 0 equals 0 plus 0. Of course, we can use this directly. Then what will happen to the induction thing? Here is our induction hypothesis. Suppose we know that a plus 0 equals to 0 plus a. So what will happen to sa plus 0? What is sa plus 0? It equals to sa plus 0, correct? Oh, sorry, no, sorry, my fault. Here we should say sa plus 0 equals to sa, according to the definition of the plus, right? And sa equals to sa plus 0. We need to add this step because if without the middle step, we cannot directly show that sa plus 0, this step equals to this step. We need the middle one. And we know that a plus 0 equals to 0 plus a, so we can set this one equals to s0 plus a. And finally, we can get 0 plus sa. Hence, we have proved this one. And finally, we can prove that a plus b equals to b plus a, again by induction. So our base case is simply set b to 0, so we have a plus 0 equals to 0 plus a, which we just proved that. And then for the induction step, what can we do? We can do, again, we need induction hypothesis. So suppose we know that A plus B equals to B plus A. Then what about A plus SB? This one equals to SA plus B, right? Here is what we can get according to the definition. And then according to the induction hypothesis, we know that this one equals to SB plus A. Because A plus B equals to B plus A. Oh, sorry, where it is? Oh, sorry, where it is? Okay, here it is. Okay, and then what happened for the next part? Okay, we know this is SB plus A, and we just reuse the definition of plus. We know this is B plus SA, right? And this is why we need to prove the lemma 1. In lemma 1, we know that A plus SB equals to SA plus B. So here we know that B plus SA equals to SB plus A. So here we are done. We prove that A plus B equals to B plus A finally. Okay, let's go to the next part of this question. The next part is A times B equals to B times A. Again, here is the definition of the multiplier we learned in class. And here is only two things we can use. Of course, we can use everything we already proved here. So let's try to prove this. Before this one, again, I want two additional lemma first. The first lemma is A plus B times C equals to AC plus BC. Here for the base case, we can set C equals to 0, so our base case is A plus B times 0 equals to what? According to the definition, this one equals to 0 directly, and 0 equals to 0 plus 0. And use it again, we can get A plus 0 plus B plus 0. B times 0, sorry. Okay, so this is our base case. We can prove this one easily. What about our induction? What's our induction hypothesis? So here it is. We need to suppose we know that A plus B times C equals to AC plus BC. Then what is A plus B times SC? According to the definition of multiplier, just use this one. We know that this part equals to A plus B times C plus A plus B, right? And according to our definition hypothesis, we know that this one equals to AC plus BC plus A plus B. And as we know that A plus B equals to B plus A, we can exchange the position of this term. So we can get AC plus A plus BC plus B. And what's this one? We just use the definition of multiplier again, and we can get A times SC plus B times SC. So we are done from the, this is lemma 3, let's call it. Okay, lemma 3. Here we call it lemma 1, here it's lemma 2, here it's lemma 3, and here, okay. And here, let's go to our next lemma, lemma 4. We want A times 0 equals to 0 times A. For base case, it's still easy. Just set A to 0, so we have this one. Right. Then, again, we want an induction hypothesis. So what's that? We can do that. Suppose we know that A times 0 equals to 0 times A. Then what is SA times 0? What is SA times 0? SA times 0 equals to 0, right? Just use the definition of multiply directly. No matter what it times 0, it gets 0. So what's 0 again? We can write 0 at A times 0, right? And what's A times 0? We know that according to the induction hypothesis, it's just 0 times A. They are the same thing. Okay, so 0 times A is equals to 0 times A plus 0, according to the definition of plus. And this one equals to 0 times SA. So we are done for the lemma 4. And finally, we can go to our last part of our question 1, which is A times B equals to B times A. So for our base case is our lemma 4 directly. We know that 0 plus A equals to A plus A, 0 times A equals to A times 0. Okay, then again we need an induction hypothesis. So we can suppose A times B equals to B times A. Then what is A times SB? A times SB equals to A times B plus A, right? According to the definition of multiply, of course. And we know that A plus B equals to B plus... A times B. We know that A times B equals to B times A based on the induction hypothesis. So we know that this one equals to B times A plus A. And which can be read as B times A plus 1 times A. By the way, if you want to use this one, if you want to convert A to 1 times A, we need to use another, we need to prove another thing. Let's call it lemma 5. Sorry, I forgot this one. So for lemma 5, we want to prove that A plus 1 plus A equals to A. Of course, we can say that it's equal to A plus 1 maybe. Oh no, we just try to prove 1 plus A. We just want to prove this one. So firstly, base case, we can say that the base case is we set A to 0, so we know that 1 times 0 equals 0. This is directly true. And the induction is what? The induction is, suppose we know that 1 times A equals to A. Then 1 times SA is what? Is equals to 1 times A plus A. Oh, sorry, not plus A. It's 1 times A plus 1, right? And 1 times A is what? 1 times A is A. We know that from the induction hypothesis. So this one equals to A plus 1. And A plus 1 is SA plus 0 is equals to SA. So we know that 1 times A equals to A. And then after we prove this one, according to lemma 5, we can do this one. We can convert A to 1 times A. And then again, we can go back to our lemma 3. For lemma 3, we prove that A plus B... we prove that A plus B times C equals to AC plus BC. So for now, we have B8 plus 1A. So this one equals B plus 1A. And what's B plus 1? We just said that equals to B plus, maybe let's, B plus 1 equals to SB plus 0, A equals to SBA. Correct? Okay, so finally we are done about the question 1. We proved that lemma 1, lemma 2, and the first part, and then lemma 3, lemma 4, lemma 5, and then the last part. Okay, then let's go to next question. For next question, we still have 2 parts. For the first part, we want to show that there is some Q and R, so that R is less than B, and A equals to B times Q plus R. And here what I do is I try to construct such Q and R. Firstly, I set Q0 equals to 0, and R0 equals to A. And what I want to do is I want to do Qi plus 1 equals to Qi plus 1. And Ri plus 1 equals to Ri minus B. And I want to redo this one several times until I finally got some R is smaller than B. So I write here, where R is larger than B, I just redo this one. And at B is always larger than 0, right? So R is keep decrease. So first thing I want to prove is that for all pair of Qi and Ri, this formula will always satisfy. So our base case is just when I equals to 0. What we have? We have Q0 equals to 0 and R0 equals to 1. Oh, sorry, R0 equals to A. What the fuck of this? Okay. And we have R0 equals to A. Then what is B times Q0 plus R0? Equals to B times 0 plus A equals to A, of course. So the base case is true. Then what is induction? What is our induction hypothesis? Suppose we know that B times Qi plus Ri equals to A. Then what about B times Qi plus 1 plus Ri plus 1? What's this one? So as we know how we construct the sequence of Q and R, we can simply set Qi plus 1 equals to Qi plus 1 plus Ri minus A. Oh, sorry, minus B. Right? Because Ri plus 1 equals to Ri minus B, Qi plus 1 equals to Qi plus 1. So we can do this directly. And then we just expand it. We got B times Qi plus B plus Ri minus B. We have these two terms. We just combine them. And then we got B times Qi plus Ri. And according to our induction hypothesis, we know that this one is A. So we are done. We know that for any I, the Qi and Ri pair will satisfy this requirement. Then the next thing is that I wonder if this one will terminate. So we want to prove that it will terminate, otherwise we may not find such pairs so that R is smaller than B. But here it's also easy. If it's not terminate, we just suppose it not terminate. It's not stop. Okay. Then what we will have? We will have a sequence from R0, R1, R2, and blah blah blah. And here we know that as Ri plus 1 equals to Ri minus B, and B is larger or equal to 1. So we know that Ri plus 1, let's write here, we know that Ri plus 1 is always larger than Ri. So we can set something like this, R3 and blah blah blah. And suppose it's not stop. This sequence is infinite. We make an infinite distance sequence, and we know that this is impossible. So we know that this suppose is wrong, and we know that this one is true. Also, remember as we learned in class, the infinite descent is just the same thing with the well ordering. So we can use the well ordering to show that there exists such Q and R. Here we set a set called R to be all the natural number which exists some Q. Remember this thing is called exist. Exists some Q so that Q times B plus R equals to A. And of course, R is not empty because we know that at least when R equals to 0, R equals to A and Q equals to 0, this one is true. So at least A inside R. So here, let's state something. Okay, as we know R is non-empty, and according to well ordering, we know that there is some smallest element in R. Let's say A is the smallest in R. A is the smallest. Then what we can get? Oh, sorry, let's not call A. Let's call it R. So let's say R is the smallest element in the large R set. Okay. And then we know that if there's some Q, that's so QB plus R equals to A. And let's suppose, and we want to prove that this R is smaller than B. Otherwise, this Q and R cannot be used because we have two requirements. One is BQ plus R equals to A. Another requirement is R is smaller than B. So let's check. Just suppose. So to prove this one, we just suppose. Suppose R is larger than B or equals to B. And we can construct another R prime. R prime equals to R minus B. And Q prime equals to Q plus 1. Here is just we construct Ri plus 1 and Qi plus 1. So we know that this R prime and Q prime will also satisfy this equation. So which means, R prime is also in R. But R prime is smaller than R. So R is not the smallest element here. So which means this is contradiction, so this suppose is wrong. And we got such R is smaller than B, and we have a Q here. Okay, next. Oh, this question have next part. We want to show that such Q and R is unequal. To show this one, we just suppose it's not unequal. So let's suppose there is another pair, Q prime, R prime. And so Q prime times B plus R, oh, what happened here? Plus R prime equals to, what of this? Okay, where were we now? Okay, here. Equals to QB plus R and equals to A. And also we know that, of course, these two things are not the same. Then what can we get? We can get something like K equals to the difference between, or maybe let's write the difference between Q prime minus Q, maybe. So as these two are different, so we know K is larger than or equal to 1. Then what is difference between R? R prime minus R equals to what? It's larger than 1K times B, right? This one is equals to K times B, which is larger than or equals to B. But here is the tricky thing. Both R prime and R is smaller than B. R prime smaller than B. R smaller than B. And also, we have this one. Both R prime and R should be larger than 0 and smaller than B, because they are natural number, of course. So we know that this one is impossible because consider here is a number from 0 to B. We just want to state 2 points here. One is R and one is R prime. The distance between them cannot be larger than B. So we know that this one is impossible and this suppose is impossible, which means this one is true. Okay. Next question. For question 3, just go to lecture 4. We already learned it in class. Go to the lecture note, read that. And for lecture 4, we want to show that square root 3 is irrational. So we just suppose it is rational. And what is rational mean according to the definition? The rational means it can be shown as A over B. Correct. Well, both A and B are natural number. And consider, as we know this one, so we can say that A square over B square equals to 3. And so A square equals to 3 times B square. And as we know that A square is a multiplier of 3. So A square has the factor 3. And here we should know that A also has the factor 3. Can you understand this one? Because consider if A don't have factor of 3, then the A square cannot have a factor of 3 because the A square have to have a factor 9, something like that. Okay, so we can write like A equals to 3A prime. There's some A prime here. And we can write like, from this equation, we can write like 9A prime square equals to 3B square. And then we know that 3A prime square equals to B square, but just divide 3 from both sides. Okay, then we know that 3 is also a factor of B square. So we know that 3 is a factor of B. And so we can get such B prime. 3B prime equals to B. And from this equation, we know that 3A prime square equals to 9B prime square. And then we know that A prime square equals to 3B prime square. And 3 equals to A prime square. So 3 is also a factor of A prime. Then, to remember this one, we just got this one, right? So we can find some 3A prime prime equals to A prime. And we just redo this whole process again. We can have some 3A prime 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 equals to A prime prime. Do you find the problem here? As of course A is larger than 0. A prime is also. So we know that as this way we can got A is larger than A prime. And here A prime is larger than A prime prime. And similarly A prime prime prime. And if we keep redoing this process, we can form a sequence like A is larger than A prime, larger than A prime prime, larger than A prime prime prime, and infinite then. Hence, as this distant infinite sequence is not possible for natural number, we know this one is wrong. So we know that this one is wrong and this one is right. And just as I said for the last question, the infinite descent is the same thing as the well ordering. So you can also try to use well ordering to solve this question. And I will list both of the two solutions in the solution I post to the Canvas. Okay, we already proved the square root 3. And another part is for square root 5. This one is simple. You can just replace all the 3 with 5 in this process, and you are done. Okay? Fine, let's go to the next question. Here is our question. We want to prove that either we can have some natural number m equals to square root n, or we want to show that square root n is irrational. What's the so we want to show that we want to prove this one. We always want to suppose this one is wrong first. So what if this proposition is wrong? Then there is no such m. And remember, the not apply for all is make the all become and square root n is some rational number, so let's write a over b. Then we can just do the similar thing. Okay, so let's do this one. Here, let's try to use well ordering to do this one. Let's suppose there is a set called large A. Large A contains all the A in natural number, of course. And for all the A, there exists some B, so that A over B equals to square root n. Okay, so as we know that square root n is not irrational for this one, it's rational. So we know that A is non-empty. And A is a set of natural numbers, so according to the well ordering, we can say that A inside A is the smallest element in A. Okay, let's just write like this. So, and it have some B, so that we know that A over B equals to square root n. And also, as no such m equals to square root n, so we know that b is larger than 1. Otherwise, we know that we can set m equals to a, and there is some m there. So what we have now? We have a square over b square equals to n. And hence, we can write like a square equals to n times b square. And here it means that b square is a factor of a square. So b is a factor of a. Correct. As both a and b are positive natural number. So what can we do? We can write a equals to b times a prime. So a over b equals to b times a prime over b equals to a prime over 1. And also we know that a prime is smaller than a. And as this one equals to square root n, so we know that a prime is also in a. And a prime is smaller than a. So a is not the smallest element anymore. Which means this one is wrong. And hence this one is wrong. And this one is true. Here we use the well ordering. And of course you can use other way, just like if you know the coprime, what is coprime is, you can do it really simple. Here I just showed another way. Okay, if we know coprime, so we can simply set square root n equals to a over b, and we set a coprime with b. And then we can know that a square over b square is equals to n. But as a is coprime with b, we know that a square is also coprime with b square. So this one is wrong. So this one is wrong. So any two way is okay. Let's go to the next question then. For question 6. Here we want to show that for all the natural number can be represented as the product of prime, and we write that POP as the set of all the product of prime. And for the converse of this one, we write NPOP. So to show this one is wrong, we want to show that there exists some A inside N. A is inside the NPOP. which means we want to show that NPOP is non-empty. So we just suppose it's non-empty, and then we select that A is the smallest element there. Of course, again, we want to use the well ordering again. Suppose A is the smallest element and A cannot be represented as product of prime. What can A be? Can A be a prime number? Of course. A prime number itself is the product of prime number. So A is not prime number. So which means A can write as B times C. And both B and C are larger than 1, which means B and C are all smaller than A. Let's write something like this. So we know that 1 smaller than B, C smaller than A. However, as A cannot be represented as the product of prime, POP, let's say POP directly. Both B and C should be inside NPOP. So what can we know? We know that B inside NPOP and C inside, all C inside NPOP. Why? If this one is wrong, then which means we can just represent B as some product of prime and represent C as some product of prime, and hence we can convert A into product of prime, and hence A is no longer inside NPOP. So at least one of B and C should be inside NPOP. However, both B and C is smaller than A. See this one? So no matter which one is in NPOP, A cannot be the smallest element. So this one is wrong. And so this one is wrong. And we prove this one. Okay, for the next question. For 8 times 8, you can just construct some way. You can just try to do it yourself, or search online, or just write some code for that. And if you are interested in the induction way, how to use the induction to prove this, you can go to the font to read. On Canvas there is a net tool, or you can go to the wiki to search for net tool. But here we don't want to discuss a lot about it. We only care about 9 times 9. Firstly, let's check how the net will move. Here I draw a small board. Consider net is here. Here is net. It is in a black cell. What can it move? It can move to here, 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 and here. Oh, yeah. So see what is interesting here? All the next step it can go is white. And suppose if this cell is white, all these cells should be black. So what can we know? For a net, if it begins on the black cell, the next step must be white. And then next must be black, and then white. And whatever. So for 9 times 9 board, we have 81 cells in all. And as we need to go through every cell and go back to the origin cell, our tool should have 81 steps. And suppose we begin in a black cell. Which color we end with? Begin with black cell, so here is first step, second step, third, fourth is black, fifth is white, and you see, on every odd step, we stop in a white cell. So which means, when we go to the very last, 81 step. Here should be a white. However, what we want after the 81 step, we go back to this one, the origin one, because our origin one is black. So this white is contradict with this black. So we know that's not possible for 9 times 9. Here is how we proved this one. Okay, for question 8, we have a triangle with side length 2, 2, 2, 2, and we have 5 points inside the triangle. So remember, we have learned the pigeonhole theory in class. For pigeonhole, we won't always have n balls and n minus 1 box, right? For now, we have 5 points. So what we want? We want to have 4 boxes with 5 balls. But we only have 1 triangle. What can we do? Okay, the best way is separate the triangle into 4 parts. Here is what I do. I just connect the middle point of the triangle. So what can we get? We can get 4 small triangles with side length 1. Okay, as we want to put 5 points inside the triangle, at least 2 triangles will inside 1 small triangle. And we know that any 2 points inside this triangle, the distance between the 2 points will be at most 1. So we are done. Here is what we want to prove. Yeah, we are done for this. And for the next question, we have 31 days for a month, and we have 64 students. And of course, everyone have only 1 birthday. And can only on 1 day have birthday. So we can convert this question into 31 box, 64 balls, and they want to show that at least 1 box have at least 3 balls. So still use pigeonhole theory. Consider if we only have 62 students. What happened where? There are 2 situations. Firstly, there is already some box with at least 3 balls. We don't care about this case, right? Because even though we add 2 more students here, this will not change this result. So this is already done. Another situation is like all the box only contain 2 balls. So because we have 31 box and 62 balls here, something like this. So this one seems not correct, but we have 2 more students. We have totally 64 students. So we want to add 2 more students. So for next student, no matter which box we add it to, it will already have 3 balls, and it achieves the requirement for the question, which is at least 1 day have at least 3 students have birthday. Okay, so here we'll finish every question inside the weekly problem 1. And here is another something I want to talk. There is a question in the Google Sheet, just like, what can we use when proof in exam? The answer is everything you learned in class. And if you didn't learn that, for example, for the question 1, if you want to use something new or something you didn't prove, you need to prove that first. After you prove it, you can use it. Or if you learned that in class, like the pigeonhole theory or like the piano axiom, you can directly use that. Or the well ordering or infinite descent. So here is this question. And also other detail for homework and other things will be published to the Canvas later, so you can check that. And this solution, the PDF version of the solution will also be posted to the Canvas. So you can also check that. Okay, I feel that's all about this weekly tutor session. Hope everyone is fine.